Stop. You're gonna make me worry about it. I just want to worry about it. Oh, yeah.
Okie dokie. Let's see. Where'd you go? Okay. So, even though I know I'm not here yet. Well, besides the sign-in sheet. Pass the sign-in sheet around. Okay, the first thing I wanted to do was a vote. So I have two different classes. I have a fundamental class and I have a college Chem 1 class. And I'm still sorting out who's in what class. I could have looked it up, but I thought I would just give both my classes this option. I have received a few emails over time about how difficult it is to keep up with everything. You know, for this class, you have a homework that's due on Monday and Wednesday, and you have a quiz due on Monday and all that jazz. So, while I'm not changing the quiz, the question is about the homework. At the beginning of the semester, I asked, did you want it twice a week or once a week? If it is twice a week, it's due on Monday and on Wednesday. If it is once a week, it'll be due on Monday. If it is twice a week, it's 5 points each. If it's once a week, it'll be 10 points each. If it is twice a week, it will remain about the number of questions you've been having. I mean, when we get to naming, there may be more just because that one takes a lot more practice. But I try to keep it reasonable. If it's on 1 day a week, you would have all the questions from what both of them would be due on that 1 day. So that is what you're thinking about. Now, before I do the vote, if anybody wants to try to convince their classmates of one or the other, they're welcome to try. But raise your hand instead of all talking at once. So I'm giving you another option here. Yes. It would get posted on Monday because or Sunday or Monday. So it's not going to get posted any earlier than it did this week. This week was the first week I've got everything back on track. So it will get posted on Monday morning and you would just have all week to do it, essentially.
Oh,
Yeah.
okay. The homework and-
Well, no, the quiz is still just, it opens Monday morning, it closes Monday evening. But the homework you would have a week.
It'd be smarter to have the one because you can work on it on your own pace that week and you don't have multiple due dates happening. It's the same amount of work, you just work on it on your own pace.
So that's one for 1 day a week. Anybody for 2 days a week? I try not to be able, and what it will mean, by the way, is I had 4 homeworks being dropped. What it'll mean is I could drop 4 5-point assignments. So the four of the ones that have already occurred, or I can drop 2 10 points later on. So in other words, it's going to be the same. The points are not going to change, but the number I could drop would change. Because instead of it being 2 5-point ones, it would be 1 10-point one during the week. So I'd have to drop half as many. Or I could drop 2 5s and a 10. In other words, the maximum number of points that'll get dropped is 20. Whichever way it goes, the maximum number of points that would get dropped would be 20. Okay, so now the vote. I'm going to have and I will do it both, or well, all 3. I will do 2 days a week, 1 day a week, and no vote, meaning you don't really care. The majority wins. I really recommend everybody either vote for the 1 or the 2 and not the don't care. Because if it's close, we'll have to have a second vote. And the way the vote's gonna work is you're gonna, when I call out the one you want, you raise your hand. We'll go through and count so that I don't screw up. As we count, you lower your hand so that I can keep up. Sound reasonable? Okay. So all those that want to move it to 1 day a week, raise your hand. Count. Seven. Okay, I didn't see a hand raise. Sorry, 7. All those that wanted it 2 days a week. I'm still getting counts, so. Okay, now I'm going to count the number of folks in this room. So that is 32. 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20, I think I did 2. So 34. So 2 people said didn't have an opinion. Okay. Who said this, it didn't matter? Okay, I had 2 no matters. So that is correct. So we will stay at twice a week. And folks, if you think I'm trying to make my life easy, I wasn't. I do listen to my students. Whether they were the ones that voted 2 times a week and changed their mind, or voted 1 time a week and still want it 1 time a week, I try to listen. I really do. Thank you. And that's all I can do is listen and see what I can do. So, but as you see, the majority rules, and so it'll stay at 2 a week. And things will be like they were this week, where everything comes up on Sunday from now on. I even make the homeworks where they're all prepared for the week. That's why I have to go in and after a class figure out what needs to be canceled, because I make the homework up front and then I have to go in and figure out what we didn't cover. But any questions for me? Okay. So today we are going to talk about the energy of light. Then we're going to get into the observations that specifically led to our, I should have said, led to rethinking the atomic structure. Those observations are the photoelectric effect in the atomic spectrum. I'm going to explain what those mean. Then we're going to talk about the Bohr model. The Bohr model resulted from these observations. And then we'll talk about the Rydberg-Balmer equation, which basically uses that Bohr model to explain a lot of pieces. Now, when we get into the Bohr model and the Rydberg-Balmer equation, one of the things that you should know about specifically the Rydberg-Balmer equation, well, and the Bohr model, is that they're actually only valid for a 1-electron system. So they're only valid for like hydrogen and helium with a +1 charge. They're not valid for very many things. But all of this is what led us to develop the quantum mechanical model, which can be used to explain every single atom on the periodic table. So now I will say, while I'm doing this, you will be using this energy of light calculation. You are going to be using, you're going to be actually determining the atomic spectra, and you're going to be using the Rydberg-Balmer equation in next week's lab. So the stuff I'm going over today is going to be directly applicable to next week's lab. And then when we get into lab this afternoon, that's when, or this morning and this afternoon, that's when I'll get into the quantum mechanical model of the atom, which will take us a few days. Not the quantum mechanical model per se, but to try to piece it all together where it's not just randomized numbers in your brain. So, okay. So on Tuesday, we began our discussion of nature of light. Light is in the form of waves, and there are three characteristics we use to describe those waves. The first characteristic we talked about was the amplitude. How large was the wave? The larger the wave, if you're talking a flashlight, the brighter the light. The smaller the wave, the weaker the light. The second characteristic was the wavelength. The wavelength is the distance between either the peaks on adjacent peaks or the troughs on adjacent waves. And then we talked about the frequency. The frequency is how many waves pass a particular point in any given time. The relationship of wavelength and frequency can be, we can perform calculations to illustrate this wavelength using the speed of light. The speed of light, c, is equal to the wavelength times the frequency. And see that the c that I gave you is 2.998 times 10 to the 8 meters per second. Remember that when you do that calculation, the units matter and the units are being dictated by that speed of light, constant. So what I have here is I have the electromagnetic spectrum. Basically, we're talking about light waves. And let's, just to give you a sense of what they accomplished. So if you look here, we have longer wavelengths going the shorter wavelengths. Now, that means red light that is visible is going to be a longer wavelength, and purple light is going to be a fairly short wavelength for visible light. But visible light is only a tiny fraction of the spectrum. Now, in here, what we're about to do is we'll talk about this energy relationship. But to help you understand the energy relationship, let's talk about each of these components. First of all, radio waves. Radio waves come in, they vibrate the eardrum. Does anything happen to your body? Does anything change within your body with radio waves? No. Now, the next thing, which isn't in here for some reason, right here is where we're going to get microwaves. Yes, we're talking the microwaves that you find in your microwave oven at home. And what microwaves do is they provide enough energy to take the water molecules in the food and get them spinning. That's all a microwave can do, is get molecules spinning. It can't do anything else. It gets the molecules moving. And it's actually that movement, that friction caused by the movement, that heats up food. Then we move into the infrared region. And then we move into visible light. Now, I wanted to point out the radio waves, the microwaves, the infrared. By the way, infrared, so let's take a bond. Infrared is only strong enough to make the bond vibrate or rotate or translate, move from one area to another. Again, it can't break bonds. So all of these from your purple light on down does not have enough energy to cause any damage to the body. Once we get past that, we get into the ultraviolet region. And we always have to worry about UV light, UV rays. Hence the reason everybody says sunscreen up. That's because the further we get this direction, the higher the energy. And ultraviolet radiation is the first form of radiation that has enough energy to start breaking bonds. Then you move to X-rays. We're told we can only get like 6 X-rays a year. The reason is due to the damage that getting an X-ray causes to the molecules within your body. And then finally, Hulk rays, the gamma rays. So let's just, now that we've gone through this and hopefully the visuals I gave you helped to explain things, let's talk about relationships. We've already discussed the fact that wavelength and frequency are inversely proportional. Basically, as the wavelength increases, the frequency decreases. How many waves past a given point in a second will decrease as the wavelength increases. Which is what we see here. Wavelength increase, frequency decrease. So what is the relationship between energy and frequency? As energy or as frequency increases, energy increases. Now, the equation, so let's talk about equations. Energy is proportional to the frequency when the frequency is multiplied by h, where h is Planck's constant. and it is equal to 6.626 times 10 to the minus 34 joules seconds. Folks, just like the speed of light is the dictator for units, Planck's constant is a dictator of units as well. Now, folks, we can, let's talk about this frequency. Earlier, I said C is equal to wavelengths times the frequency. We can rearrange this equation where frequency is C over the wavelength. If we take that and plug it in for frequency, then another way we can calculate energy is that energy will be equal to H times C over the wavelength. Or in other words, the energy is Planck's constant times the speed of light divided by the wavelength. Again, the constants dictate units. Always, the constants dictate units. So, examples. Calculate the energy and wavelength of a photon of light with a frequency of 6.165 times 10 to the 14th hertz. Remember, so let's talk about what we want. We want to calculate the energy at some point, and we want to calculate the wavelength at some point. But we are given the frequency of 6.165 times 10 to the 14 hertz. Remember that hertz is the same thing as per second. Those are one and the same thing. Now, if we want energy or wavelength, and we're given the frequency, then two of the equations we will want is energy is equal to H times the frequency. And we can use the speed of light is equal to the frequency times the wavelength. Yes, you will be given the equations and the constants on the test. You have to know what equation to use when, what constant to use when, but you're given them on the test. So let's talk energy. So our energy is equal to H times the frequency, and our speed of light is equal to the frequency times the wavelength. So other things we're going to need here is we're going to need the H, which is 6.626 times 10 to the minus 34 joules times seconds. And we're going to need the speed of light at some point, which is 2.998 times 10 to the 8 meters per second. Those are things that our equations are telling us we need. So let's work on the energy. The energy is going to be equal to H times the frequency. So our energy is equal to 6.626 times 10 to the minus 34 joule seconds times the frequency we were given, which was 6.165 times 10 to the 14 per second. You will notice that the seconds are canceling out, leaving joules, and joules is one of our common units of energy. When you calculate this out, you would get an energy equal to 4.085 times 10 to the minus 19 joules. For our speed of light equation, C is equal to the wavelengths times the frequency. We can get to the wavelength because the speed of light divided by the frequency is equal to the wavelength. Our speed of light is 2.998 times 10 to the 8 meters per second, divided by the frequency, which was 6.165 times 10 to the 14 per second. And that will equal our wavelength. And again, the seconds cancel. So you are left with meters, which is a unit of length. And it comes out to be equal to 4.863 times 10 to the negative 7 meters. One thing you should always check, I did not ask in this particular question, but you should always go back to your question. I've said it before. You should always go back to your initial question. Make sure that you gave the answer, got all of your answers, and also one common mistake is make sure that you have given me the answer in the units requested. In this particular case, I didn't request a specific unit, so you could give it to me in either unit, meter, nanometer. But if I request a specific unit, make sure you give it to me in that unit. Questions? So let me give you one to do. And if you're not getting my exact answers when you key something into the calculator, it's probably how it was keyed into the calculator, so. And I have a calculator that was left in my office. Okay, so for the wavelength, again, you would use C is equal to the frequency times the wavelength, or C over the frequency is equal to the wavelength. So that would be 2.998 times 10 to the 8 meters per second, divided by the 1.5 times 10 to the to the 15 hertz, or per second. And that would give you the 1.999 times 10 to the minus 7 meters, or 199.9 nanometers. The energy, you would use energy is equal to H times the frequency. So your energy is equal to 6.626 times 10 to the minus 34 joules seconds times 1.5 times 10 to the 15 per second. And that gave you 9.939 times 10 to the minus 19 joules. Folks, when you think about what this means, when I say it's 199.9 nanometers, this is 400. Well, this is 400, so just below that, about 390. What it means is we have gotten into the ultraviolet region to get to 200 nanometers. And what you're doing is you're saying, okay, I have ultraviolet light, and it's going to be the energy associated with this wavelength is that 9.939 times 10 to the minus 19 joules. Now, why is that important? Because again, if you'll recall, I said, once you get into that ultraviolet light, you start having the energy where you can break bonds, which can mess with cells. You're able to actually do this type of calculation and determine if the energy was sufficient enough. So this is ultraviolet light. The one before it was because it had a wavelength of 486 nanometers. The wavelength before it at 486 nanometers is going to be in around this region, so it gets into the blues. And what you were calculating when you calculated the energy is how much energy the wavelength was at that point. Any questions? Yes. No. Only the beginning material. You will in the lab, but not here.
So how many decimals do you want to match the constant?
Match the constants and match the constants in the data. In this particular case, if I wanted to do it to a sig figs, I should have recorded this one as 2.0 times 10 to the minus 7 meters and 9.9 times 10 to the negative 19 joules. That would be the correct number of significant digits. So yes, you take into account the significant digits of the constant, but you also have to take into account the significant digits of the data to figure out your sig figs.
The hertz on the equation, and I see that you didn't like put that unit anywhere. Is that almost like
No, what you have to remember, and I'm going to put this in the middle, but I'll do it in blue, mainly because I've already got stuff below there. Hertz equals seconds to the minus 1, which equals per second. They're all the same thing. So the fact that it's hertz, it's the same thing as per second. I like to change it to per second because of the constants. Questions? Okay, so now we're going to get into the observations that led us to go, that's interesting. What does the atomic structure really look like? I mean, we still know the protons and the neutrons are in the nucleus, so this is really talking about where are the electrons. And the first observation is the photoelectric effect. So with the photoelectric effect, what we have here is we do have a device, and you will notice we have let's see if I can draw on this thing. We have a metal surface, which they have gone over here and drawn that metal surface so that you have a better vision of what's going on. Now, on that metal surface, they expose it to radiant energy. It hits the surface and it causes electrons to break free. Those electrons, folks, that's what's going on in the lights above you. Is a metal is being exposed to an energy that causes the electrons to break free. And the electrons are traveling from one end of the light to the other end of the light, giving off light, giving off energy. Now, when classical physics, or when physicists were looking at this from a classical physics standpoint, they noticed that, okay, I shine radiant energy, it gives off an electron. So they were like, okay, let's try this other energy. So they would do another energy and nothing would happen. Or let's do this and nothing would happen. So they were going, okay, so on those particular cases, if nothing is happening, then according to classical physics, what we would need to do is simply increase the size of the impending wave. In other words, increase the amplitude. And they were like, okay, if we just increase the amplitude, we'll get it to work. It still didn't work. What they noticed is it only worked at certain wavelengths. What those wavelengths were is that the wavelength had to be at the correct energy in order for it to happen. So again, they exposed that metal to all sorts of energy, or all sorts of radiation. But only if it was at or above a very specific threshold would anything occur. Had to be at or above that threshold for anything to occur. I'll come back to that thought in a minute when we get to explaining more about what's going on. This is just another picture of that, what was occurring in that photoelectric effect. Again, we shine energy. It has to be at or above a specific threshold of energy. And what would happen is we would knock an electron out of the metal. But it has to be at or above a specific threshold of energy. Now, another observation that led us to go, about atomic structure was what is known as the atomic spectrum. If I were to take this white light and I were to expose that white light to a prism, what would I see? A rainbow. And according to classical physics, that's what you would predict for light. but that is not what we observed, depending upon the element. In this particular case, I have a hydrogen lamp, which you will be working with next Thursday. This hydrogen lamp is being excited by electricity. And then if you think about it, light is just being given off. So you see this full array of light. What we do is we pass that light through a spectrometer. Basically what we're doing when we do that is we're not changing the light, we're just simply narrowing it through a specific slit. So it goes through these slits to kind of narrow the beam so that it is focused directly on a prism. Now, that light, as it passed through the slits, was focused on a prism, but instead of getting a rainbow, we got very specific lines associated with the atom and the element. One line that, to be quite honest, is impossible to see with the devices that we have and typically your eye, because most people just can't see it, is at 410 nanometers. One line is a blue-violet light, which is tricky to see, but you can see it at 434 nanometers. One line is a blue-green, which is very obvious at 486.1 nanometers. And then you have a bright red line, which is also very obvious at 656.2 nanometers. But we don't get an entire rainbow. We get very specific colors. So photoelectric effect, atomic spectra did not follow what physicists using classical physics would have expected. So that is where Bohr comes in with his Bohr model. And this is a little bit different, but it gives you the gist. Essentially, you have your nucleus. And just like the planets orbit the sun, Bohr suggested that the electrons orbit the nucleus. And you have very defined orbits that they travel, where the little blue dots represent our electrons. Now let's see why or how this actually explains the photoelectric effect and how it also explains atomic spectra. So, you have energy that comes in, and it strikes an electron. If that energy is at the correct threshold, then that electron will be completely ejected from the atom. But it has to be the correct threshold in order to get out of the orbit. I mean, think about it. It's like, I'm drawing a blank as to a great way to explain this, but basically a marble. Let's take a bunch of marbles. Think of marbles on just like this little circle. If you shoot a marble at this, it has to have the correct amount of energy if we want it to completely leave the circles, right? Because if it doesn't have the correct amount of energy, it's not going to be able to leave the circles. So the photoelectric effect is the same thing. You have to give it the correct amount of energy at in one instance, for this electron to be completely ejected. It has to be at one instance because electrons do not store energy. The electron itself does not store energy. It has to occur all at once because the electron doesn't store energy. So this model made sense for the photoelectric effect because you had to impinge that, the energy impinging on that electron had to be of the correct threshold in order to completely knock the marble out of the orbits. Any questions about how the photoelectric effect, how the Bohr model helped to explain the photoelectric effect? Now, let's talk about the atomic spectra. Okay, you got to realize that it's when you take that hydrogen lamp and hook it up to electricity. First of all, that hydrogen lamp does not just contain one atom at a time. It contains multiple atoms. The electricity is coming in waves. What happens is initially this electron, now the energy that comes in when we're talking about the atomic spectra is insufficient. It does not reach that threshold where it'll eject electrons. Instead, the energy coming in has just enough power to excite that electron, to excite an electron to a higher level. Now, folks, you cannot see this particular transition. This is atomic absorption. What you see is as the electron relaxes, let's have it relax to energy level 2. As the electron relaxes to energy level 2, let me do it a little different. That relaxation sends off a wavelength of energy that you can see. Now, the electron in this third, the one that's up here, it can relax to the second level or it could go all the way to the first level, and the wave is going to be different depending upon which level it relaxes to. The wavelength will be different depending upon which level it relaxes to. So when we're looking at an atomic spectra, you've excited an atom of an element, you've excited the electron so that it jumps to a higher orbit or an outer orbit. You cannot see that jump to an outer orbit. But then as the electron relaxes to an inner orbit, it gives off energy that you can see, that you can detect. So for our photoelectric effect, the energy we're talking about, if I can, apparently I didn't do it. For the photoelectric effect, the energy that we're discussing is the energy to take an atom of an element and make it a cation with a plus charge plus an electron. where the electron is being ejected from the atom. That's the photoelectric effect. This energy is called a specific type of energy. It is called the ionization energy. And we'll talk a lot more about ionization energy after we really understand the atomic spectrum and where everything is located. Now, with respect to the atomic spectra, I said it depends on where it is, where it relaxes to. And I'm sorry that the wording is horrible. So again, we took an electron here, we excited it to some energy level further out. You cannot detect that excitation. What you detect is as it relaxes. Now, if it relaxes all the way back to the first level where it started, that is called the Lyman series, and it gives off ultraviolet light. In other words, this is the nasty light that's given off. The next one, you can't see the lines. There's lines right here. They're in pale green. If it relaxes to energy level 2 first and pauses at energy level 2, then you get visible light called the Balmer series. That's the light that we can see with the naked eye. If the electron relaxes to the third energy level, we're going to get infrared. Now it's going to be near infrared, meaning it's going to be closer to the red light, but it's infrared. And it's called the Passion series. The Bracken series is if it relaxes to 4, and the Fun series is if it relaxes to 5. These are just, so you've excited your atom, you cannot see the excitation. It just means that the electron travels from 1 to some level out there. And then as it relaxes, it gives off light of various energies. Now, all of it's being given off at the same time, folks. It's just you can only visibly see the Balmer series. The rest have to be detected using instrumentation.
What is this model called?
This would be an atomic spectrum model. Mm-hmm.
Does that mean it changes the element itself?
It makes it an ion. Right. It does not change the idea. Okay, so the question was, when that electron pops off in this photoelectric effect, does it change the element? It changes the element from being neutral to being an ion, but it does not change the identity because you did not mess with the protons. Now, the Bohr model of the atomic spectrum of hydrogen led to 2 individuals, one named Balmer, which is what the series is named after, and one named Rydberg. It led to Rydberg and Balmer developing an equation that allows you to predict pieces of information about the transitions. That equation is 1 over the wavelength is equal to R times 1 over n sub f squared minus 1 over n sub I squared. R is the Rydberg constant. Now, folks, I've given you the Rydberg constant as 1.097 times 10 to the minus 2 per nanometer, because in lab, the spectroscopes you will be using to see these transitions for the hydrogen lamp is going to be in nanometers. But realize that we can perform metric to metric conversions. And so it could be reported in meters instead of nanometers, or kilometers instead of nanometers. It's just, I've given you the constant where it's in nanometers. But you're going to get the same constant. It's just going to have a different 10 to the power, depending upon what the unit is. N sub F is the final orbit. Where did it come to rest? And N sub I is the initial orbit. Where did it fall from? So 1 over the wavelength, which is the color that's emitted, the color that you see, times 1 over the N sub F. If we are able to see it in the visible spectrum, then N sub F is 2. It's always 2 if you can see it in the visible spectrum. N sub I is, where did it start? Did it start at 6 and fall to 2? Did it start at 5 and fall to 2? N sub I would be, where did it start from in its descent? So something important to note, because if you do the optional homework, you'll see me give this information. If it says it gave off ultraviolet light, then N sub F had to be 1. If it says it gave off visible light, then N sub F has to be 2. And if it gave off infrared light, the N sub F I'm talking about is 3. Because I'm talking near infrared. So let's look at a problem. For a hydrogen atom, calculate the energy of the photon that would be emitted for visible light where the electron relaxes from energy level 5. So looking at this, I see visible light. That word is telling me that my N sub F is equal to 2. The next thing I notice is relaxes from energy level 5. That means that's where it's starting, right? So in that case, my N sub I keep doing that. My N sub I is equal to 5. Now, the only equation that has energy levels in it, the only equation that has energy levels in it is the Rydberg-Balmer, or a version of which I'll show you in a minute. So let's do this. 1 over the wavelength is equal to 1.097 times 10 to the minus 2 per nanometer times 1 over 2 squared minus 1 over 5 squared. You can, if you need to, you can always do it in pieces. If that will help you. I don't usually, I just key it all into my calculator at once, but it can be done in pieces. And I get a 1 over the wavelength equal to, oh, I goofed. I was wondering what was wrong with that. I get a 1 over the wavelength of 0.0023037. Now to get the wavelength, if you're not familiar with it, you can use your inverse button on your calculator, which is the x to the minus 1. And it will give you the wavelength. I have to find it again on this calculator. And that comes out to be 434.1 nanometers. It is nanometers because the only unit in this entire thing was nanometers. Now, I can calculate, I could use this information and use the equation I already have, which is energy is equal to HC over lambda to calculate my wavelength, my energy. Or there is another way to calculate energy. And the other way you can calculate energy is a version that is similar to the Rydberg-Balmer equation. In this case, energy is equal to negative 2.18 times 10 to the negative 18 joules times z squared over n sub f squared minus z squared over n sub I squared. We've already talked about what n sub f and n sub I are. The z is the atomic number. We've already talked about that previously. We've talked about mass number and its notation and atomic number and its notation. Z is the atomic number. Looking back at the problem, it was hydrogen. So Z is equal to 1 because it's hydrogen. Our n sub f was equal to 2 and our n sub I was equal to 5. So the energy is equal to a negative 2.18 times 10 to the negative 18 joules times 1 squared over 2 squared minus 1 squared over 5 squared. And you get an E value of a negative 4.578 times 10 to the minus 19 joules. This equation is more accurate really than using E equals HC over lambda in case you are not dealing with hydrogen. You can use this equation for any element, whereas the other one is only valid for hydrogen. if you use the wavelength from the Rydberg Balmer, you can only, then to get the energy, you're really looking at hydrogen, whereas this equation would work for any transition for any element. So I really recommend knowing this equation for the energy when you're talking about a transition. Now, folks, I do want to make note that negative, you cannot have negative energy. You've either got energy or you don't have energy. Think about your own body. You've either got some energy or you're just blue. You don't. You can't have negative energy. It's a physical impossibility. This negative means energy is given off. Which makes sense. Because light was emitted. If these two words having some, with these two words given off and emitted basically being synonyms. So if I were to go back up to this right here, okay. If I were to go back to this right here and I were to come in, that would be a plus energy because this electron is going to be absorbing it. That electron going to a higher energy is a plus energy because the electron is absorbing. But it's when that electron relaxes and that light is given off that it's a negative energy. So you got to keep that in mind. Absorption is plus energy, given off is negative energy. Okay. So, right about time too. We are going to deal with quantum mechanics today in lab. Now, folks, I am going to forewarn you, come prepared to take notes. But most likely, until we get into electron configurations, those notes are going to be, you're going to go, huh? So don't panic at the end of class today because you're not going to have a meaning to put with the quantum mechanics until we get into electron configurations. And then I think the meaning will become more clear. But don't panic on me because it's coming. It's just, it has to be, we got to build to it. I will see everybody in lab today. Make sure you sign the sign-in sheet if you haven't already.